Hey everyone, my name is Raesetje Sefala and I'm a research fellow at the Day Institute. So today I'll be talking about like what goes on when you're creating ground truth data sets or like when you're solving AI for social good type of problems. So my focus will be on ground truth data sets. However, I've worked on different projects in different organizations in the past, and mainly my job worked around solving sort of problems or exploring solutions on AI for social good type of problems. So these are some of the organizations I've been a part of working in this direction. So just to give some motivation on why data sets in particular are quite important. We are researchers. Mainly, we are usually machine learning researchers. And when we use machine learning sort of solutions to try solve problems, data sets are usually a problem. Machine learning algorithms require a lot of data for them to be able to mimic the reality that's in the world. And as such, if we're trying to apply these solutions to real-world problems, we need a lot of data. And for these niche type of problems, gathering data sets is a very big problem. So we try to find ways to actually answer these questions that we might have and try to find like interesting sort of techniques to help us still arrive at solutions around that. So to just give you to just backtrack a little bit, what we mean by ground truth data, this is the reality. The ground truth is the reality that you want your model to eventually be able to reproduce or to mimic. So data sets, these are like labels. When you're training your machine learning models, you have to have these labels so that they have to understand what the mandate is, something to learn from. So these are the ground truth data that I keep referring to, and yeah. So to just give you a sense of what they usually look like, is that given so the images at the bottom show internal organs of the body. So if you want to train a model to maybe detect heart defects, for example, then you have to actually show the model images of hearts and images or like labels somehow of what a heart looks like or where the heart is in the image. And you have to show these multiple images. So you have to show these models multiple images so that it eventually learns the pattern, where the heart is, and then eventually what a heart defect looks like. So if you have a data set, like a satellite image, for example, a satellite image data set, for example, and you want your model to be able to learn what a neighborhood looks like, or what a house looks like, or what a stadium looks like, whatever, you're gonna have to show it images, maybe satellite images, and then labels of what you're actually interested in. So just gathering these hundreds of thousands of data points is usually very labor intensive, given that you have to coordinate people to actually label. Actually, the green parts, the labels, so the green parts, the blue parts, given hundreds of thousands of images, you have to coordinate this huge labor, like a lot of people to label these. And these labels have to be coherent. So everyone has to label all the stadiums in green, for example, for all the thousands of images. And coordinating the people and the data set itself is usually very expensive. And for some data sets, like your satellite images, that change very frequently. I mean, if you imagine maybe today the house wasn't there, and then 10 days later, there are like new houses, so these data sets would have changed. You're gonna need to do regular updates on your labels, which is very financially expensive. And just coordinating the people labeling these data sets requires a lot of evaluations. And sometimes specific people of specific domains, for example, if you're labeling, you're creating a heart defect detector, you're gonna need a doctor to actually say, this is an image of a heart defect, or this part is it denotes a heart defect. So sometimes it requires people of specific domains, on top of the fact that we need lots and lots of these data points. So that's why it's quite a challenge just to gather ground truth data. However, today I'll be talking about some case studies that I've worked on that look into, well, instead of coordinating a huge group of people to label these data sets, are there data sets that are already available, but for certain purposes that we can repurpose to help solve our problems? And then in the other case, we're looking into other like pre-existing algorithms or techniques that we can use to help solve different problems, and how effective can they actually help us create these ground truth data sets to help us solve specific research questions. So, okay, given a data set that looks like this. This is a part of Jakarta in Indonesia. So in this image, you'll see it's like an intersection. Jakarta has a very bad traffic problem, and because of that, people have like evolved into trying to find a way to just get to where they're going. So if you see this part of this image, you'll see a motorcycle moving against traffic, which is very unsafe. But then this is just one example of like the sort of chaotic scenes that you might see looking at traffic footages in Jakarta, Indonesia. So in this project, we wanted to find a way to generate labels so that we can then inform some questions that maybe we want to answer. So this is a project that I did when I worked for the Data Science for Social Good Fellowship in Chicago, but we did it in collaboration with the Pulse Lab of Jakarta and the Smart City initiative by the government of Jakarta. So the goal of the project was to improve traffic safety in the city. However, we just had CCTV footage of different intersections in the city. So the government wanted to find interesting ways to use this wealth of CCTV footages that they have in the city. There was no ground truth data to help us solve some of the requirements. However, we wanted to explore using existing algorithms to help us answer some questions. So just some context on the problem. The city of Jakarta has been growing quite rapidly, more than the government can actually support. So more people are moving into the city center for jobs or like school and other things like that. But then the government had not really planned for such a high rate of urbanization. So you see scenes like these on like prime time for going to work or coming back from work, where in this case, there's like a group of motorcycles somewhere. Some people are everyone is trying to move through the intersection, but then there's like these dangerous scenes and like for both pedestrians and people who are actually on vehicles. And they wanted ways to help manage improving traffic safety in the city. So, Okay, so to just give some context, they had over 5,000 CCTV cameras in the city. Um, these cameras were not owned all by the government, so they had access to this data set, and then they wanted ways to, can we revert to the old slides? Sorry about that. Okay, I'll just continue from here. So currently, their system was very simple. So this is what they were doing. They had someone to actually look into each camera, like manually. So someone was employed to look through these cameras in the city and then record the types of infractions that were happening. So a car moving the wrong way, they would write it down. At this particular intersection at this time of the day, the traffic jams were at this particular intersection at this time of the day, and then they would write it down. So this was very inefficient because they had a lot of cameras, and then just scaling this way would have been very difficult. So our solution was to use machine learning to look at these cameras simultaneously, and then give some information after that. So our solution involved, given a CCTV footage, can we really just try to understand what kind of objects are in the scene? Are these objects moving or are they not moving? And if they're moving, where are they moving in the scene? So, okay. Perfect. Let's see. Okay, cool. So these were some of the risks the government was actually interested in solving. So they wanted to find cars driving the wrong way. They wanted to find out where people were illegally parking, where street vendors were occupying sidewalks, because when a street vendor is occupying the sidewalk, then it would force pedestrians to actually move on the road, which was very not safe. And sometimes you'd find motorcycles that are not moving on the road and they're moving on the sidewalk. So that would also force pedestrians onto the road. That would make the scene unsafe. And the types of interventions that they were interested in were things around how they could manage where to put traffic lights in the city strategically, at what times can they deploy their limited resources of traffic officers, for example, and how can they actually plan to use their budgets that were very restricted, like where do they strategically expand roads or put circles or things like that, and how they can plan traffic sort of transport in the city. So yes, so given their cameras and the solution that we proposed, this is how we actually did it. So to help understand what types of vehicles were on the road, we actually used object detection models to find where and what vehicles are in the scene. So we wanted to know is it a motorcycle, is it a car, is it a truck, and where is it in the scene? So we used this. At the time, YOLO was like the best model. So we used YOLO. It was a deep learning model. And the reason why we used deep learning for this task was because it was relatively fast to create these labels, given that this is a CCTV footage. So it ran, like, it was streaming the scene like the whole day. So a model that is able to quickly classify and detect where these vehicles were was very essential for a task like that. So one problem with the YOLO model was that it was not actually trained on some objects that would be locally found only in Jakarta. So it was trained on it wasn't trained to detect things like tac-tacs or like food trucks and other minibus taxis and other objects like that. So these are some of the problems you find when you deal with these sort of societal impact in sort of different countries type of problems. So sometimes the scene is just generally different and data sets are not enough. So what kind of decisions do you actually make to help you get to solving the problems that you wanted to solve? So for this case, because our models couldn't actually identify these minibus taxis and these food trucks or tuk-tuks and things like that, we had to hand label, coordinate like a hand labeling journey, and we had to hand label all these images, like a smaller subset of these images, so that we can fine-tune the models so that eventually they can also include those labels at a higher accuracy of detection and classification. So before that, we would have, when you have a minibus, for example, it would be classified as a bus 10% of the times, and then other things. But then when you had like a food cart, food cart, for example, our model would just classify it, not detect it, or classify it as other things most of the time. And this was very inaccurate because there were a lot of these instances in Jakarta, and not retraining our models to identify those objects would have actually missed the whole point of the problem that we're trying to solve in the first place. So after fine-tuning the models, the model was actually able to actually pick these up, and we were able to also evaluate some of these things. So so now we can detect the objects and we know where they are in the scene. So another step would have been, because these are videos, we would have wanted to know if a car that we detect is moving or not. Because if it's moving, then we can actually not detect that as a problem. But if it's just stationary in an intersection like this, that could be causing like a traffic jam or something like that. So understanding if the vehicles that we find or the objects that we find are moving or not was very essential to that task. So we used another computer vision sort of technique called Lucas Canard method for optical flow to find out whether objects are moving or not in the scene. And if they're moving, we would record that. And if they're not moving, we would still record that. So finally, to understand whether or not these objects that we find moving or not moving in the scene are on the roads or on the sidewalks, then we used a semantic segmentation technique to understand that. So given a motorcycle, to understand if it's moving on the road or on the sidewalk, then this method was actually very helpful in helping us understand that. So that is the first project. We tried to use different algorithms to help us understand the ground truth. So given a video, we would pass it through the first model where we would detect the objects and classify them. And then we'd pass it through the second model where we would detect whether it's moving or it's not moving in the scene. And then we'd pass it through the third part of the pipeline where we identify where it's moving in the scene, so that at the end we would have a solution that says a motorcycle is moving on the sidewalk, and it would flag that. Or a car has stopped on the road, and then it would flag that. And then eventually that would actually accumulate into 50 cars were stopped at this intersection this month, so that for the next month, the government can actually say, okay, 50 cars or around 50 cars stop and at this particular intersection at this time of the day? Can we send a traffic officer at that intersection at that time to just understand why things are not moving in that phase? Or motorcycles usually move on the sidewalk in this part of town. Can we put barricades or something like that? So those were the interventions that we were able to afford the government, given solutions like these. So for the second project, usually you would find that there are data sets that are available, but then they answer specific questions. So maybe people in a certain domain would be collecting some data for a specific thing, not necessarily answering your question. So there are a lot of these data sets as well. So in the second project, we tried to understand if we can actually adapt those data sets to actually help us solve specific problems that we would be interested in. So here, we wanted to classify residential neighborhoods according to their types in South Africa. And then for this task, we actually didn't have ground truth data relevant to solve these research questions. So we wanted to augment existing data sets and then solve the problem that we had. So to just give you some context, this was a project that I did as part of my master's, actually. However, I'm continuing with it. I'm still working on it at the institute that I work for. And it looks into some of the problems that South Africa used to have, and they still has, but we want to see how those problems have been evolving over time. So some context again. So there was apartheid in South Africa. However, apartheid has ended. After apartheid has ended, we want to know if the government is actually doing anything to sort of redress some of the problems that were faced during apartheid. One of them was this notion of townships and how they were underfunded during apartheid. So some resources like your hospitals and your schools are actually overpopulated, and they were underfunded during apartheid, and they served a lot of people. But that was during apartheid, and that was the system. And now, after apartheid, we still see resources like your schools and your hospitals are overcrowded, and they look like they're underfunded. So we wanted to understand if this is actually what is happening. Are they overcrowded and underfunded? And then to understand that, we had to firstly understand where these neighborhoods were. So this was the data set we didn't have at all. So townships during apartheid, you knew where they were, but after apartheid, the current government actually merged these neighborhoods with neighborhoods like suburbs as one thing. So now you couldn't actually say, I want to research or I want to analyze what's happening in townships only, because they were merged with suburbs. So this was the second project that we had. So we had to create this data set that labeled the individual neighborhoods that we're interested in, so that we can understand these problems. So to just show you what a township generally looks like from a satellite image or an aerial photograph, the image at the top is of a township, and the one on the right, the first image, is a suburb. So the top part is a township next to a suburb, and the bottom image shows a suburb next to an informal settlement. So this is more or less how suburbs, townships, informal settlements would look like in South Africa, generally across the entire country. So we wanted to understand firstly how much they extended, like these townships, so that we can say, okay, given that this township extends until this part, what's actually happening within this sort of demarcated zone? So the data sets that we had were satellite images of South Africa from 2011. We had this data set that denotes, it sort of just shows you where all the buildings were in South Africa. And then you had this data set that shows you what the land was supposed to be used for. So each red dot in the image at the bottom shows you a house. So this part, this densely populated part, is a township, actually, next to a suburb. So yeah, this is a suburb. This part over here is of a suburb, actually. So similarly, these are the labels that we have. The data set would tell us where the townships are in yellow, and in blue, it would show us where the small holdings were, or the suburbs were, or the industrial zones were. And in red, it would show you where the informal settlements were. But then the data set is actually refined. So before this data set, the yellow part was light blue, was dark blue as well. So after we had to hand label the parts where the townships were, and then this is the result of what the data looks like now. So to just try to understand how we can train a machine learning model to help us denote where the neighborhoods were. Firstly, we had to define what a neighborhood is. So a neighborhood in this context would be where buildings were, and then it would have a certain physical sort of visual characteristic. So firstly, we had to find where the buildings were and create this data set that tells us what the land is supposed to be used for, where the buildings are, so that instead of saying maybe that whole green part at the top there is a farm, then we would define farms by the visual characteristics of what their buildings would look like. So eventually, our data set would consist of satellite images and the ground truth data. So the white parts, these are the backgrounds. So where there are no buildings, this is the background. And then the yellow would be where the townships are. The light blue would be where the suburbs are. The green would be where the farming neighborhoods were. And the red would be where the informal settlements were. So actually, the nice thing about this data set, given the data set that was given by the government, that was available and was given by the government, the one at the top right corner, our data set at the bottom actually shows you neighborhoods defined by the fact that there should be a presence of buildings there. So given a satellite image like that, instead of saying that blue part is of a suburb, our data set was actually able to define suburbs by the presence of buildings. So not just saying the blue part is supposed to be used for suburbs and there are probably buildings of suburb type. Our data set actually said these buildings are of type suburb. So this is very important when you're training machine learning models, because you are just showing a machine this image at the corner and you're saying all of this is a suburb. But then if there are empty parts that are not developed, like that part over there, then the models get confused. So if you're saying the whole part is of a suburb, but then there are non-developed parts, there are no characteristics the models can actually learn from. So that is actually a very big problem, and our data set actually helped solve that problem. So we used machine learning models that looked into classifying individual pixels instead of like an entire image, mainly because in an image in one image, maybe you'd get part of it being of suburb and then the other part being of township. So because of that, we couldn't just label the entire image as one class. We had to sort of look at a more finer way of classifying it. So given the actual image and the ground truth, these are the kinds of results that our models are able to achieve. So you'd see that given a the image in the middle row of a township, it would confuse parts of it as suburb, but then most of the image would be classified accordingly. So given the 12 classes of images that we had, our model was actually able to compare to like some of the best models for similar types of problems in the world. So, yeah, and let me just, but then there were some problems that our models would actually face. There are some failure cases generally, and some of them actually would be around some neighborhoods being classified as others. For example, the small holding neighborhood at the corner here would be classified, confused with a village, although it's not a village. But then failure cases like that actually show the reality of how things are in the real world, that you can't just say, given a data set of an entire country, you can't just, there are some similarities or some confusions that even a person labeling what the correct labels could be, just from visually looking at the characteristics, could get wrong. So these are some of the things. When you have a big model, when you have a model looking at a data set that stretches across like a big scale, it is easy if things are not consistent in reality. So, which is actually what you would generally expect in the real world. Things are not as uniform as you might think. Suburbs in Portugal, in the northern part of Portugal, might not look like suburbs in the sort of southern parts of Portugal visually. So these are some of the things that you constantly have to think about as you're building solutions in the real world. Things are not always as black and white or as clear as maybe we think about them. Things actually do have variations. So some of the things that you also think about are, how do I recognize that there are variations in my model, and how do I change my models accordingly to actually be able to capture all those variations in a correct manner. So some of those solutions are around working with people who are local to the problem. So people who actually live in Portugal, for example, would be able to pick up very quickly what a suburb in the north versus a suburb in the south would look like, rather than when you have like teams with not so diverse sort of people. It would be very generally a little bit difficult to understand some of these nuances. So this is an example of like everything in this blue boundary is of a suburb, but then the suburbs at the top right part, they have bigger yards compared to the suburbs at the corner here. So the suburbs at the corner have smaller yards, but then it doesn't actually disqualify them as not being suburbs. So some of these variations are some things that we also experienced when we dealt with our problem. And as a result, we decided you could actually make different decisions according to the kinds of errors you're seeing with your model. But then the one that we took in this case was to just collapse the classes, and instead of having classes that would show you in a more finer way suburbs, small holdings, and XYZ, we just had like neighborhoods that are wealthy, neighborhoods that are not wealthy, and things around that. So after doing that, we had other problems still. Although we solved that problem of classifying, there were these problems that arise where our models were very sensitive to false positives. So the model in the middle was sensitive to walking paths, and they would associate them with non-wealthy neighborhoods. So this part, the one in the middle actually, on the sort of the the right part of it, even if you're a human looking at it, you might think there might be a neighborhood there, although it's just part of a mountain. And then the model in the middle would be very sensitive to that. But other models we trained were not so sensitive to false positives like that. So these are some of the problems that you actually face when you are building models for like big data sets. I mean, everyone wants a big data set, but once you get a big data set, you still have like these variations that may occur, and you should be able to evaluate those variations. So at the end, we had models that we were able to use. So given images of 2011, this is how the non-built up, for example, the first column shows the non-built up pixels in South Africa. So from this whole column being non-built up in 2011, these are the new classes that were introduced where there were no buildings before. So we are able to see that in one province in South Africa, where the capital is, the parts that were not built up before were then converted into mostly wealthy neighborhoods, and then a smaller part of it, the green part, is just the growth of the non-wealthy neighborhoods that were built up in that province. So those are kind of the information we were able to deduct from the models that we built. And given images from 2011 like that, we wanted to be able to capture the growth of these neighborhoods over time. So from the graph at the graph that you saw before actually showed you given land like that, it was able to capture the change in 2017 like that. So these are some of the downstream tasks that we use for like building models that are able to detect neighborhoods. Given 2011 images, these are the ground truth labels we had. So these were where the gray part is where all the buildings were. And then looking at images from 2015, this is what our model, this is of 2017. This is what our model is actually able to predict. So it's able to see what kind of growth has happened in this neighborhood, for example. I mean, you can imagine the amount of work that goes into creating ground truth data like this. Given an entire country, someone has to actually look at the country and see where the buildings are and then label it accordingly. These are a lot of images and they cover a lot of space. And it takes a lot of time as well to just say, okay, this is neighborhood X in 2011, and then the same amount of effort and say this is neighborhood X and this is how it's grown, and then in another year, you still capture the same growth. So given models like these ones, now we are able to actually say, okay, maybe the effort would be labeling images from 2011. But then to just look to label the growth, to capture the growth of the other years, can we actually use machine learning models to actually do that for us? So as to reduce the amount of cost and labor that goes into problems like these. And maybe the only cost that could remain would be around evaluating how well the model was able to capture these growth or these changes. So some key takeaways from using machine learning for sort of social good problems involve the fact that when you work with real world data, you need like thorough evaluations, not just technical evaluations, but also qualitative evaluations, and maybe the people from that place or domain experts who've been working on that problem, they also need to take a look at your results and see how well it actually reflects the reality on the ground. because otherwise it doesn't really, maybe it won't be solving the problem as you think it may be. So it's a very iterative process as well. So it's, I mean, you might think creating sort of machine learning solutions involves getting data and then building the model, and then yay, you have a solution. But then it's actually more around getting the data, creating the model, and then seeing that maybe what the model is reflecting is actually not what is happening in the real world. Do I change the data or do I change the models? What if I change the data? What other cost does it involve? Do I need to get more people to relabel and things like that? And then do the whole data model and then evaluation again, and then see if it's actually reflecting the reality, and then go back again and change something, maybe with the models, and then do it again until you actually get it right, which is very expensive usually. But then, you know, it's like, the expensive things usually are the technical mistakes you might be making, not involving domain experts and talking to people early on in the project. And also one sort of underplayed thing usually is that the data exploration on problems like these can be emotionally disturbing. I mean, during the project in Jakarta, we would see weird things in these video footages as we were exploring them. Sometimes, even in the South African project, you'll see informal settlements on a riverbank, maybe. And then when you look at the same spot a few years down the line, the people are no longer there. And then you ask yourself what could have happened to those people who were there and things like that. So, yeah, solving sort of societal problems using machine learning is quite an interesting process, and it's not just about creating data at all. It's not just about building the models at all. It involves a lot of things around the people you are solving the problem for, also the data sets that are available. How do you also communicate, or how do you understand the results that you're seeing? Are you able to actually pick up the errors, and are they actually errors from the model, or are they nuances that maybe you don't understand? So working with people from that domain or people who live in those places can actually help you with understanding things like that. Thank you. If there are any questions, yeah.
Any questions for Raesetje?
Hello, thank you for your presentation. It was very interesting. I think you use a lot of creativity in your work, and I think that's amazing. And about that, I would like to ask you, in generating these kinds of data sets, like ground truth data sets, you reported some trouble in sometimes classifying some satellite images. Did you ever think about, instead of using just satellite images, you use two sorts of data to correctly classify? For example, you show the images that were just a mountain or something like that, and it would be confused with the neighborhood, right? What do you think about if you use, I don't know, communications data to know, oh, I don't have communications from that location, maybe I can confirm that that is not a neighborhood. Or you look at a neighborhood that is richer. I have some kind of information that indicates that that is actually rich and not poor. Do you ensemble data sets, if I can say it like that?
Mm-hmm. Yeah, no, absolutely. That's how we think about it. Usually because we need to be able to evaluate. Usually we would use them for evaluation. If there's not enough of that kind of data set, we would use that part to evaluate the models. Because, I mean, as much as there are data sets that we work with, just because real people live there and there are a lot of changes and variations that might be happening. Having like a layer like that to help us evaluate what could be actually, what the ground truth really could be, helps us a whole lot, and we do that. I mean, in the last project that I shared, we also had like we're also looking into using survey data sets of like the general wealth of places, the cost of real estate in a neighborhood, to help us determine whether or not our model was getting it right, and other proxies or other sort of auxiliary data sets like that to help us evaluate, mostly because we don't have usually those data sets for like the years, like all the years that we maybe are looking into, or maybe the specific places, parts of the country that are there. For example, maybe we might not have real estate costs for informal settlements, for example, but then we would have real estate costs for suburbs. So to evaluate whether or not our models got the suburbs correct, we might use a data set like that for suburbs. But then for informal settlements, we might use something else. Maybe we might use transport data to see how like the movement within like a small place, as a neighborhood like an informal settlement, the frequency of movement versus in a suburb, or that might not be useful so much for farm neighborhoods, for example. But yeah.
We have time for one more question. Then Raesetje will be in the showcase. Any other questions?
At the back.
Thank you for your keynote. My question is, what happens after the conclusion of your projects? So, for instance, for the city of Jakarta, did the city implement measures to fight the issues you found? And if so, what did they do?
Your question, you're not very clear, but then your question is around what happens after we complete.
Yes, your projects.
Yeah, actually the one by Jakarta was implemented by the government, but then because, see, this is actually why it's very important to get ethical things correct when you're creating a solution for a certain place. It's very important to have these conversations around what you want your models to be used for and things like that. Because, for example, in our case, in Jakarta, it was a particular government at the time that was using our solution. So after elections and all that, the government changed, and the new people in power were not the same people we delivered the solution to. So as a result, our solution was no longer used by the next government, mainly because, some reasons could be around, for different projects, could be around whether the use policy that the developers had when delivering the solution. Maybe there could be conflicts around what the solution should be used for, and then it's pulled out and things like that. So that was actually a very interesting one, because the solution that we delivered, depending on how governance on it is set, it could be used to invade people's privacy whatsoever. So the people who are creating the models and all that have a big responsibility in making sure that the solutions that they're delivering are very ethical, because these are real people that you're delivering solutions for, and things around that. But yeah, the one for Jakarta, it was actually implemented, but with the changing of the government, the solution was no longer used. And then the one for the South African project, we are still actually working on it, but then the data sets are given to NGOs who look at different problems, but use this data set and other domain experts in health and geography and places like that.
Okay, thank